For me, it's a great pleasure to visit Grenoble again. So some years ago, I came here for a 1-month visit, and it was really nice, very pleasant stay here. After that, I come some other times, and of course now I'm very happy to be here for the celebration of the Annales de l'Institut Fourier. So thank you for the invitation. So this is going to be a talk about minimal surfaces. So I'll try to survey at least one aspect of the progress that we made in recent years. So of course there's a well-established theory about minimal surfaces in Euclidean space, but this is not what I'm going to talk about today. So here I try to look at say the general problems when you look at Riemannian manifolds, and you try to understand some universal principles that basically force minimal surfaces to exist. And basically in the past few years there was some rapid progress. Basically now we know that there are lots of minimal surfaces in Riemannian manifolds. In this talk, I'd like to emphasize one aspect of that story, which is the more theoretic aspect. So I've tried to explain one theorem that the way I'm going to state actually follows from the combination of works of some different authors. So it's going to be, of course, a talk about Morse theory. So of course, then you have to tell me what the space is and what the functional is. Well, in my case, the space is going to be the space of closed hypersurfaces, say sigma n in some Riemannian manifold, dimension n+1. And then I want to look at the area functional. So of course, critical points of this functional are a minimal hypersurfaces. Right, and what's the theorem? So for reasons that will become clear later, I'm going to assume always that the ambient dimension is between 3 and 7. This is basically to guarantee that the critical points are going to be smooth surfaces. So the theorem that says that for a generic metric, so generic here is in the sense of usual sense of bare. So for most Riemannian metrics in the sense of bare, and you can take them to be in the smooth topology. So for generic Riemannian metric G, of course generic is natural because I want to do Morse theory. There exists, and for some constant that depends only on the dimension, C of n is to be positive. Okay, C of n is a dimensional constant. There exists a sequence, say sigma k, k equal to 1, of smooth, closed, and embedded. They're always embedded in this theory. Minimal hypersurfaces. Such that first, the Morse index of sigma k is equal to k. So there is one minimal hypersurface for every Morse index. the areas, if I take the ratio of the area of sigma k by k to this power here, 1 over n plus 1. So take the limit. This as k goes to infinity. This is equal to the constant times the volume of the ambient manifold raised to the appropriate power here, which is n plus 1. And we also know that these surfaces are dense in the manifold. So if I take the union of the sigma k's, if I take the closure, this is the whole manifold. Okay, so this is the theorem. And well, in Moore's theory, you have to talk about what the topology of the space is. So this is the space of cycles, which is closely related to the notion of volume spectrum, which I'm going to define later. So in this subject, we're always considering the point of view of geometric measure theory. Okay, so the surfaces are not given by maps. They are thought of as objects by themselves. And technically, the space of hypersurfaces, we denote it by Z. And the notation is like this. So technically, this is the space of n-dimensional mod2 flat chains sigma, which are boundaries. So the boundary of something. Flat chains in M, of course, which are a boundary. So if you want, you can think of this as some Lipschitz surfaces with they have a well-defined notion of boundary. In this case, of course, the boundary is 0 because it's the boundary of a boundary. So if you want to just think of this as a space of hypersurfaces that are boundaries of open sets, for instance. And again, for this discussion, taking coefficients modulo 2 is going to be crucial. I'll explain why in some minutes. So this is my space of hypersurfaces. And the key thing to understand the topology of this space is to consider the boundary map. So the boundary takes some domain. So this is the space of domains. Of course, returns a cycle, right? So U goes to the boundary of U. But the key thing is that this is a 2 cover, because if I'm taking coefficients modulo 2, so if a hypersurface is the boundary of some region U, then the only other domain whose boundary is equal to sigma is the complement of U. So it's a 2 cover. And the space of domains is actually a contractible space. So one way to see this is by, if you choose your favorite Morse function, say, so here's the manifold M. You can choose, say, a Morse function, maybe taking values in the unit interval. So here you have the level sets of F. So if you give me a domain U, I can deform the domain by just intersecting, say, with the sublevel sets of F. So this is a well-defined deformation that basically sends everything into the empty domain of the trivial domain, if you want. So the space of domains is contractible. And this is a 2 cover. So this is pretty much like the projection from a sphere into a projective space. So the same way you actually calculate the homotop groups of a projective space, you can use here, because you can lift maps from the space of cycles to the space of domains. And you see that just like in the case of projective space, the fundamental group is going to be Z mod 2, and all the higher homotope groups are trivial. So in fact, in this case here, the space of cycles, from the point of view of homotopy theory, is actually an infinite dimensional projective space. So this is like the projection from the infinite dimensional sphere to the infinite dimensional projective space. The infinite dimensional sphere is contractible. The antipodal map is just the map that sends a domain into the complementary domain. So this is really nice topology. You see, it doesn't even depend on what the manifold is. It's always an RP infinity. In particular, we have RPKs here for every k. So we can talk about non-trivial k-parameter families of hypersurfaces inside the manifold M. And as I said, mod 2 here is crucial because, one can do the same kind of thing for, say, integer coefficients, but in that case, this is going to be a z-curver. So the map will be like the projection from the real line to the circle. So the space becomes just a circle. And then you can hope to construct one minimal surface, but not more. But forgetting about the orientation, you suddenly have this structure, so you can hope to find infinitely many minimal surfaces by exploiting this homology here, and of course doing Morse theory. Right. So the theorem, this theorem really represents the state of the art until very recently. So there was a theory initially developed by Almgren in 1965, and then finished by Pitts in 81. And what the theorem says is that, again, supposing that I'm in the range, again, suppose I'm in this range here, then there is always one minimal hypersurface. There's always a smooth one smooth embedded minimal hypersurface for any metric here. So G, of course, doesn't have to be generic because I'm not saying anything about the Morse index here. So there's always one minimal hypersurface. This was what was known back in 1981. And if I'm in higher dimensions, so this, if due to work of Shen and Simon, we know that if the ambient dimension is at least 8, then the theory works, but the minimal hypersurface can be singular. Okay, so we have that the sigma can have a singular set, but just like in the standard Plateau problem, one can bound the dimension of the singular set. So the Hausdorff dimension of the singular set of sigma is always bounded by n minus 7. So the singular set has to have codimension at least 7 inside sigma. Okay, so this is also sort of 81. But then more recently, joint work with collaborator Andre Neves. So this is the year the paper was posted on arXiv. We started considering this sweep out, so multi-parameter sweep outs. So we started using this structure to produce more minimal hypersurfaces. So the first thing we did actually in this paper, we proved that if the Ricci curvature of the ambient manifold is positive, then there exist infinitely many minimal hypersurfaces. This was the first result. And later, I'm going to talk about that later, we are able to show that for generic metrics also there are infinitely many minimal hypersurfaces. So the case for general metrics was settled by Antoine Song, so he's a PhD student of mine. This is a paper 2018. So one can construct infinitely many more hypersurfaces for any G. Okay, so we know that there are always infinitely many minimal hypersurfaces. When I say minimal hypersurfaces, I always mean smooth, embedded, closed minimal hypersurfaces. Right. But of course, when the metric is generic, then we can hope to really do Morse theory in the sense that we can hope to characterize the Morse index and say more about the structure of the set of critical points. So, yeah, so let me explain how to do that. So first I will say more about the topology of the space of cycles. It turns out that there's one way, kind of like explicit way of saying this structure is by considering the following map. So let's say f is a Morse function from the manifold to the unit interval. Then I can consider the following explicit map, lambda, which goes from Rp infinity to the space of cycles. And what you do is, if you give me a point here, so it has homogeneous coordinates, say a0, a1, ak, and then zeros. So what you're going to do is you're going to build a polynomial in f with this list of coefficients. So you take the polynomial a0 plus a1f ak f to the k. So this is a function on the manifold. You look at the set where this is, say, is non-positive, and you take the boundary of that domain. Okay. So the boundary is basically the zero set. You can see that if I multiply these numbers by any non-zero real number, the zero set stays unchanged. So this is really well defined in Rp infinity. And it's actually, what this is doing is actually simple to describe, right? Because I mean, this polynomial has some roots. And basically, the image here is going to be the sum of the level sets of f corresponding to those roots. But because you're taking mod 2 coefficients, those roots that have even multiplicity, they will cancel out. So basically, you're looking at the level sets of f corresponding to the roots with odd multiplicity. This is a cycle. And it's easy to see that this is continuous in the flat topology. I forgot to say, this is the topology here, of course, crucial, is the so-called flat topology. And what the flat topology does is it measures the volume in between the surfaces. So if I draw a picture like this, maybe this is a sphere, but maybe it can have a genus 1 surface like that. In the space of cycles, so the flat topology will measure this volume here. So in this picture, you can see that they are very close to each other. Okay, so it's nice because from this point of view, you don't predict what the topology of the hypersurfaces will be, okay, because they all live together in this space. So this is continuous in the flat topology. And what the lifting argument will tell you is that this induces isomorphisms on all homotope groups. So in topology, say that this is a weak homotope equivalent, so which is enough for our purposes, because in particular, will tell us that the cohomology groups, the space of cycles, are the same as cohomology groups of Rp infinity. So if I take the kth dimensional cohomology group, everything here is with z mod 2 coefficients, okay? This is like hk of rp infinity, which is z mod 2, and this is generated by k power. Okay, so lambda bar is a generator of h1, and lambda bar of the k is the k power of lambda bar with itself k times. Okay. So lambda bar has geometric meaning. So let's see how do I do this. Table 2. I have to do one. Okay. Go together. Okay, so the fundamental cohomology class, that's lambda bar, has geometric meaning. So what it does is the following thing. So if I'm explaining what lambda bar is. So if you give me, this is a degree 1 cohomology class. So if you give me a loop of hypersurfaces, so if I take sigma, this is a loop, so say sigma of 0 is equal to sigma of 1. Then what you can do is they are all boundaries, right? So I can start with the initial hypersurface. There are two choices for the domain. So you pick one, and then once you pick one, there's a unique way of extending that continuously, right? So I can write sigma of t as the boundary of u of t, where u of t varies continuously. So when I return here time 1, you basically get that the boundary of u of 1 is going to be equal to the boundary of u of 0. Therefore, either u of 1 is the same, is equal to u of 0, or they are complementary domains. Right? And then the cohomology class evaluated at that loop is going to give 1 if the domains change, if they exchange, right? So if the omega 1 is the complement of omega 0. And it's going to be 0 otherwise. So this is cohomology class that detects the non-trivial sweep-outs of your manifold. If you want those families of hypersurfaces that when I lift to the space of domains, the lift is open rather than closed. Okay, so this is what lambda bar does. And then its k powers generates the whole cohomology of the space of cycles. So once we know this, we're going to look at the families of hypersurfaces that detect that cohomology. It's not enough to consider RPKs. We have to generalize that. So here's the definition. Say X is the parameter space. It could be any compact simplicial complex. And then you say that the definition, you say that a map phi from X to the space of cycles, it has to be continuous in the flat topology. You say that this is a k-sweep out if it detects lambda bar to the power k. Okay, so the definition is that when I consider the pullback of lambda bar to the power k, I get a non-trivial element in hk of x. So this is the definition of what a k-sweep out is. So the example would be the map lambda restricted to RPK in that particular definition there. If I restrict lambda to RPK, it's going to be a k-sweep out. Yes? A question?
It's cohomology.
Sorry?
It's cohomology.
Cohomology, yes. Oh yeah, thanks. Cohomology group. Right. So those are examples. Let me say that phi belongs to pk when this is true. And then what you do, now you consider all k-sweep outs, and you do a minimax. Okay, so you define the k width, so definition, the k width of M is the invariant. So it's a geometric invariant. Definition is you look at, so it's a minimax. So you consider all k-sweep outs. Notice that the domain of the sweep out depends on the map. Okay, it can vary. So for each sweep out, I maximize over the domain the area function. So this is the definition. Right, so you can see that from the definition, you can see that a k sweep out, sorry, a k plus 1 sweep out is also a k sweep out. So this sequence of numbers is actually ordered, and this is what we call the volume spectrum of the manifold. Volume spectrum of M, the metric is the sequence, say omega 1 less or equal to these numbers are positive, okay? Omega 2 is the volume spectrum of Mg. So these numbers actually somehow go back to Gromov, but he was not looking at minimal surfaces or geometric measure theory. What he was doing actually, his definition was different. He was looking at the way he was thinking about hypersurfaces was a zero sets of functions. Okay, so you give a function on the manifold, and then you consider its zero set. And then, of course, the space of functions is a vector space. Again, if I multiply this by a non-zero real number, the zero set stays unchanged. So this is really like an RP infinity again of hypersurfaces. So one can look at this point of view, define the corresponding minimax numbers, and he was interested in how these numbers grow. Okay, so he proved that they actually grow with the power k over 1 over n plus 1, but he conjectured that something like that will hold true. This is actually a crucial ingredient that allows us to prove these results. It's called the Weyl law for the volume spectrum. This is a theorem that we proved with Jokumovich, myself, and Neves back in 2016. We proved that Gromov's conjecture is true. So namely, if I take the limit of the k widths normalized by this power of k, I get the constancy of n. So the theorem is that there exists some constancy of n, positive of course, we want, such that this is true. So, you know, this is like the question of like here in the shape of a drum, but here instead of frequencies, you're sort of hearing the areas of minimal surfaces. But I should emphasize, of course, this is inspired by the usual Weyl law for the spectrum of the Laplacian, which is very similar to this, but differently from the case of the Laplacian, we do not know the constant, so it's not known. It's possible to estimate the constant, but to compute it explicit is difficult. Okay, so in the case of the Laplacian, you know the constant is the same for all manifolds, so you can pick your model, like the round sphere or maybe a flat torus, compute eigenfunctions, and see what the constant is. But for minimal surfaces, it's kind of like a nonlinear problem, so it's very difficult to classify all minimal surfaces in any given space. Even if I give you a round sphere, it's basically impossible to know the whole list. So we do not know what the constant is. But of course, this is related to minimal surfaces because, as I said, this is the area of a minimal hypersurface. That's what the minimax theory of Almgren and Pitts gives us. Okay, so the minimax theory tells us that for each k, so for every k natural number, there exists a minimal surface, but the minimal surface could be disconnected. Okay, so there's going to be a disjoint collection, say sigma 1, k, sigma, depending on k, you can find a disjoint collection of connected minimal hypersurfaces. They're all embedded, and a family of integers. These are called the multiplicities. Such that the k width is the weighted area of this component. So it's going to be the sum of m1k times the area of sigma 1k plus so on qk, k area sigma qk. So these numbers are called the multiplicities. In some sense, this possibility of multiplicities is similar when you consider the problem of closed geodesics. It's similar to the problem of getting a geodesic iterated many times. This is something that you do not want because you want to construct different geodesics, say. So there's a similar problem for minimal surfaces here. Namely, these surfaces are produced by a limiting process using geometric measure theory. And what can happen is when you take a limit, your surfaces could maybe develop some neck, like in this picture, and converge, say in this case here, it would be converging to two copies of the component sigma. And in fact, there are examples where this can happen. But with Andre, we conjecture the following thing. This is called the multiplicity. One conjecture. We conjecture that generically, so for a generic metric, multiplicities are always equal to 1. Okay, so these numbers they're all equal to 1 for a generic metric. This is some years ago, and when I say there was a rapid progress, so this conjecture was already proved. Okay, and I'm going to state that next. So let's see. So maybe let me keep this statement on the board. So first, in order, towards this theorem, with Andre we did work on the Morse index. Okay, so we proved this was in 2015. We proved that the Morse index is bounded from above by k, by the number of parameters. So here the Morse index is really the sum of the indices of the components without regard to multiplicities. So we proved that if I take the sum of the indices, the components, this is always bounded from above by k for general metrics. And then in another paper, 2018, we proved the lower bound if the metric is generic, which is because everything here is inspired by what happens in finite dimensional Morse theory. But in our case, we have to develop new techniques because this is not a Hilbert space or anything like that. So we have to do things by using other methods. But we proved that here that for generic metrics, or maybe I should say not for generic metrics, what we proved was that if the multiplicities are equal to 1, so if multiplicities are equal to 1, then we also have the lower bound. So in fact, it has to be equal to k. And finally, as I said, we have a proof of the multiplicity 1 conjecture. This was first done by when the dimension is equal to 3, the ambient dimension, by Choros and Mantelidis. But they were not using this version of the theory, the Almgren-Pitts. They were using some other variant, which is called the Alenkhan variant, which is more PDE-oriented. But anyway, in the setting that we conjecture, this was proven in the full smoothness range by Xinzhou. This was in 19. So really using the Almgren-Pitts variant that I'm talking about. And he was using some previous work of himself with Jonathan Zhu. But anyway, we do have the information that generically the multiplicities are always equal to 1. So therefore, our previous work holds true. And then we have these two statements here, right? So for each k, we have a minimal surface whose index, the sum of the indices, the index is equal to k. And the area of that surface is equal to the k width. Where is that? So the multiplicities are equal to 1. So the sum of the areas of the components is equal to the k width. Therefore, by the Weyl law, we have that this ratio converges to the volume. So the remaining thing to prove is density of these surfaces. I hope that you can still see here. So it remains to prove density. It's too much. So in fact, in 2017, we proved the following theorem. This is joint with Erie. Levitz. So we proved that for I'm assuming that I'm in between dimensions 3 and 7, and then we prove that for a generic metric on M, the union, if I take the union of all minimal hypersurfaces, again, closed, embedded, and so on, this union is dense in the manifold. Okay, so not only there are infinitely many minimal surfaces, but they cross every ball, so they're sort of everywhere in the manifold. So at the time, we proved this for the union of all minimal hypersurfaces. But there might be minimal hypersurfaces that do not come from the volume spectrum. And in fact, that's what happens in some examples, like S3, the round 3 sphere, for instance, that's what happens. So I'm stating here an improvement of that. So I'm saying that the surfaces realized in the K widths are dense in the manifold. So I'd like to explain the argument here. To prove this, we need a modification of the argument of this paper due to my PhD student, Yang Li. So I want to explain the argument, because after you sort of do all the work, the principle is simple to explain. Maybe try to finish with that. So yeah, so the idea is you give me an open, I want to prove density, right? So density. So you give me an open set in the manifold, and you give me some natural number k. I'm going to consider, let's say that M, script M is the space of all Riemannian metrics on M. And then given the open set and the natural number k, I'm going to define a subset of M called mu comma k. And this is the set of metrics on the manifold such that the condition is that every minimal hypersurface sigma in M with that metric, and such that the area of sigma is equal to the k width, and the index of sigma is less than or equal to k, I'm going to require that every such minimal hypersurface must intersect U. Okay, satisfies the condition that intersects U. So this is a collection of metrics, and it's by using some compactness theorem that I don't have time to go into details, but using some compactness theorem, it's easy to see that this is open. Okay, because the idea is that if I look at all minimal surfaces with bounded area and index, that space is compact, at least in the so-called the varifold topology, but it's compact. So this has to be open, because otherwise you would be able to find a sequence of metrics with surfaces satisfying those properties, but that stay outside U. So you'd be able to take a limit of the surfaces. You would get a surface for the limiting metric that does not cross U. Okay, so it's a standard argument. So it's open because of compactness theorem. This is always open. Of course, the interesting part is to see that if I take now the union over all k's, so the claim is that now I have the open set fixed, so U is fixed, and I consider now the union over all k's of this set. The claim is that this is dense in the space of metrics. Okay. So why is that? Let me sketch the argument. You start with an arbitrary metric, G in M. choose a neighborhood of G, say in the C-infinity topology. I want to construct a metric in the neighborhood that belongs to that set. So what you do is first you perturb G to be bumpy. Say G prime. So bumpy means that every minimal hypersurface is a non-degenerate critical point. So this is a variational problem, right? You can compute the hashing of the area functional. We have a quadratic form. If that quadratic form has no kernel, you say the minimal surface is non-degenerate. And it turns out that by work of Brian White, bumpy metrics, a generic metric is bumpy. So for a bumpy metric, the area functional behaves like a Morse function. Every critical point is non-degenerate. In particular, minimal surfaces are isolated. So you can always perturb G to be bumpy, and then we have this condition. So this is going to imply that for the bumpy metric, when I look at the following collection, I look at the collection C of all areas possibly with multiplicity here, but integer multiplicities. I consider all minimal hypersurfaces, sigma tilde, in my metric. I look at all possible areas, even if I consider integer weights. When the metric is bumpy, this is a countable set. Okay? Why? Because, well, by the compactness theorem, if I bound both the area and the Morse index, this space of minimal surfaces is going to be finite because they are isolated. So for every fixed bound, I have finitely many minimal surfaces. Of course, I can let the bound grow, and I get at most a countable set of areas. So what you do is you have your manifold M, some open set U. So I'm going to perturb the metric by bumping the volume up. So you choose a function, say, with compact support in the open set, say a non-negative function that is not trivial. Okay. And then I'm going to define the following perturbation of G prime. I'm going to multiply G prime by a factor, which is 1 plus t times f. Okay, so because f is positive, I'm increasing distances here, so the volume goes up. And say I'm going to consider t in some interval 0 delta. So because I want to stay inside my neighborhood, V. And what you do is, well, the volume goes up, right? So the volume, so let's say if I am time delta, the volume goes up strictly. So if the volume goes up, the Weyl law will tell us that some width has to go up also, because otherwise we would have a contradiction. Right, so the Weyl law will say that there exists some k, which I don't know, such that omega k also goes up. But notice that the way I defined my perturbation, the metric outside U stays the same, right? So G prime of t coincides with G prime outside U. So the minimal surfaces that stay outside U stay minimal. So they're right. So I have the same minimal surfaces outside U. So what's going to happen is that when I look at my k width, it's strictly increasing, and it's not difficult to see that the k width is a continuous function. So because it's strictly increasing, it has to assume uncountably many values, right? So a whole interval of values. So for some time in my interval here, the k width will not belong to C. Okay, maybe I'll stay here. So because C is countable, there exists some time in the interval such that omega k of m g prime of t bar does not belong to C. Well, but I know that so if I now consider any minimal surface with that area, in that metric, right? If I now consider any minimal surface with that area, so the area will not belong to C, therefore the minimal surface cannot stay outside U. Because if it stays outside U, they're the same minimal surfaces as for G prime, the set's countable. So this minimal surface automatically has to cross the interval. And then we prove that every minimal hypersurface with this condition intersects U. So therefore, by definition, my metric G prime of T bar belongs to the union of those sets. So this proves density. And then to finish the argument, what you do is you just use a countable basis of open sets. Say UI in the manifold. And then you consider the collection you consider the for every UI I have my set. They are open and dense, so if I intersect this on I get a residual. It's a residual set in Baire sense. So therefore, a metric in this intersection is generic, and by definition, for every I, so for every I, G hat is going to be for every I, G hat is going to be to some MUI KI. And when I do minimax for the KI width, I will get essentially a minimal surface with those properties. So that minimal surface we have to cross the open set. So I always get a surface coming from some K width that intersects the open set U. Okay, so this finishes the proof of density. And you might ask about higher dimensions. Let me just end the talk with a statement here, because I'm always restricting to dimensions between 3 and 7. This is a theorem again of my student Yang Lee. It says that if n plus 1 is greater than or equal to 8, then for a generic metric G on M, there are infinitely many minimal hypersurfaces with optimal regularity. They are not smooth, but they will have this codimension 7 singular sets. We don't know whether they become dense. This is open in high dimensions, but at least we know that they're infinitely many. Okay, stop here. Thanks.